This is an ellipsoid. It's an egg-looking thing. That's what we're going to be talking about. We're going to be talking about quadratic surfaces. But let's start with something that we know, conic sections, slices of a cone. So this is the sort of where I want us to be, but in 3D. When I look at this x squared plus y squared equals 9, or when you look at this x squared plus y squared equals 9, you go, oh, that's a circle, center 0, 0, radius 3. I know what this looks like. I can see the shape by looking at the equation. This parabola, I mean, it says parabola here, but even if it didn't, you'd go y equals minus 2x squared. Oh, that's an upside down parabola. That plus 1 moves it up. It's an upside down parabola. The 1 moved it up 1, and the 2 made it a little bit skinnier than normal. We can just look at the equation and see the shape. I look at this, oh, that's a hyperbola. That's another conic section, right? If it's a plus in the middle, it's a circle or an ellipse, right? I have circle down here, which is just a different kind of ellipse. If I put, or a special kind of ellipse, if I put a 4 in here, I'm going to take it out in a minute, but if I put a 4 in there, that's an ellipse. All I've done is squish one of the axes. It's gone because it says circle. I want them to be the same. If there's a minus in the middle here, then I know it's a hyperbola. And I've got a graph of a hyperbola there. So those are conic sections. Now notice everything's either squared, the x squared and the y squared, the x squared and the y squared, or only one of the things squared. Now that's a regular parabola that I put. It's an upside down because of the minus, but it's a parabola where the x is squared. If, I'm going to change it, if I did this, it's still a parabola. It's just a sideways parabola now. But with one of them squared and one of them not squared, I know that's a parabola. Let's put it back the way it was. My point is that we're familiar enough with these shapes and these equations that the name is, I can see the name, I can see the equation, I can see the graph all in one chunk. Let's go 3D then. Quadratic surfaces. So it's the same idea, but now I have to add a z component. So just like with the conic sections, the x and the y, there's only 2 variables because we were just graphing in 2D. Now there's 3 variables because I'm graphing in 3D, x and y and z. They're either all squared, x squared, y squared, z squared, or one of them's not squared. So the one that maybe is squared or maybe is not squared, I've written as a z. That's what the bracket to the 2 means here. Maybe that's squared, and in some they're squared, like in the ellipsoid. In some they're not, like in the paraboloid or the hyperbolic paraboloid. Anything with the parabola word in it, part of the word in it, has the one of the variables not squared. It's not always the z. Just like up here, when I switch this one around, it could be the y not squared or the x not squared. It just changes it into a sideways parabola. It's just the fact that one of the variables isn't squared that gives it that parabola flavor. Same thing here in 3D. If one of the variables isn't squared, it's going to give it a parabola flavor to it. The slices, the level curve slices. So ellipsoid, everything's squared. Hyperboloids, everything's squared. Just like ellipse, everything was squared. Hyperbola, in 2D, everything was squared. Anyway, so this is like a general form. Some number x squared plus some number y squared plus some number z, maybe squared, maybe not, plus a number equals 0. That's sort of the general form. Now, one thing you might be wondering, like, how come I go A, B, C, J? What happened to D, E, F? You could have some, this could be a shifted quadratic surface, so maybe there's like a D, X, E, Y, like unshifted, just like you can move parabolas around. you can move these quadratic surfaces around. We're just sort of looking for general forms right now, the easiest form. So I'm not including those pieces. We're not, right now we're not thinking about that. So let's look at these general shapes. And where I want us to be is the same place that we are in 2D. I want you to be able to see the equation. Like I ask you, here's an equation, what shape is that? And you go, oh, it's an ellipsoid. Or draw the thing, sketch the thing. Well, okay, that's, when I say draw it, you're going to be drawing in 3D, that's hard. Using a program to actually sketch the thing in 3D, I wouldn't ask you to do that without, using a program. What I could ask you to do, though, is sketch level curves, sketch slices of it. So let's look at this equation, this ellipsoid. And the oid kind of means like 3D. So more than 2D. Let's look at this ellipsoid and see how I can think it's why do I think it's the shape that it is? Well, if I want to make it sort of more familiar, let's move this z over here. The z squared piece over here. Now I've got what looks like an ellipse, right? Some number x squared plus some number y squared equals a number. If I take a slice at a certain z, like I make z equal to a number that's a level curve, I can't make z equal to 5, because that would give me something squared plus something squared is equal to, if I make z equal to 5, minus 24. So you can't have positive equals negative. So right away, your z is locked in between the biggest it could be is 1 and the smallest it could be is minus 1. Oh yeah, the biggest it is 1, the smallest the z is equal to minus 1. That's at the tip. You can pick any number of z and you'll get a slice. If I were to pick one, so for instance, and I know I got to pick, let's pick 0, because that's easy. If I pick 0, I've got 2x squared plus 4y squared is equal to 1. That's the shape of an ellipse. If I picked z equal to, I don't know, a half, that'd be 1 minus a half squared, 1 minus a quarter, 1 minus a quarter is 3/4. It would be 2x squared plus 4y squared is equal to 3/4. It's just a different, smaller ellipse. Every time I take a slice, it's an ellipse. And I see that's these bands along here taking a slice, ellipse, ellipse. Let's take that slice by just, right now my viewing window is from 3 to minus 3 for the z's. I'm going to tighten that up. I'm going to make that minus 0.01 to 0. So that's like I'm narrowing in my viewing window. It's like I'm setting, the picture will look like I made z equal to 0. And yeah, I'm getting that ellipse. That slice is an ellipse. To take a different slice, wow, okay. Let me put this back. If I take a different slice, I'll get a different ellipse. Smaller at the tip to its maximum when z is equal to 0, all the way to its bottom. So I'm looking at the equation and thinking about level curves. Now I took the slice in the z. We could have taken the slice, let's put that z back. So I'm putting the equation back the way it was. I could have taken that slice in the, in the x, so I'm going to specify x. So I'm going to pick x to be a number, move that over, and I can see that something squared plus something squared, this also has to be positive. So the biggest x could ever be is 1 over root 2. The smallest x could ever be is minus 1 over root 2. But every time I pick an x, I plug in, I get a number, I just get another ellipse. I'm going back to the same picture, but now my slices are like this. Slice, slice, slice. Just to sort of hammer home then, I'm going to reduce my x in the same way. I'm getting ellipses in that slice as well. Slice like this ellipse, slice like this ellipse, slice like this ellipse. It's an ellipsoid. Every time I take a slice parallel to one of the planes, the x plane, the y plane, the z equals 0 plane, I'll get an ellipse. Let's put it back. There's charts. When you have like a, well, as you do, a multivariable calculus book, you can look and they've got charts for these, but let's sort of catalog all this. I'm not keen on memorizing a chart because that's a lot of work and I'm going to forget. This level curve thing, idea of taking slices, I think that's the way to go with this. So I don't have to memorize anything. I already know the conic sections. By taking slices on the, by making x equal to a number, a constant, y equal to a constant, taking those slices, I'll get the conic sections that I already know. Okay, next one, paraboloid. The paraboloid, same idea. If I make, let's say I make x equal to, or z equal to, let's start with a slice. I'm going to make z equal to a number. What's the smallest I can make z equal to? Well, it's x squared plus y squared equals z, so z's got to be positive. The smallest I could ever make it is 0. So right away, this shape doesn't have anything below the z equals 0 plane. Say you make a z equal to 4. That'll be x squared plus y squared equals 4. That's a circle. So any sort of valid place where I make z equal to a positive number, every slice is a circle, and as z gets bigger, the radius of it gets bigger. So think of, what's this paraboloid shape? It's a stack of circles, and the circles are getting bigger and bigger. Let's see what it looks like. This will be a paraboloid. So I'm going to change in here. That's going to be x squared plus y squared equals z. Oh yeah, there's my stack of circles. It's a paraboloid. If I take a slice this way, I'm going to get a circle. If I take a slice this way, I'm going to get a parabola. Taking a slice this way is making y equal to a number. Taking a slice this way is making x equal to a number, also going to get a parabola. Let's look back here. If I make y equal to a number, now I'm getting z equals x squared plus some number. That's just a parabola moved up. Likewise, if I make x equal to a number, say I make x equal to 1, that's going to be z is equal to y squared plus 1. It's the parabola moved up 1. Those are my slices. Every time I take a slice, it's the parabola moved up a bit. So I can think of this shape as a stack of circles or a stack of a stack of parabolas. It's a paraboloid. Now, stack of circles, if I go in here and I'm gonna multiply that. I'm gonna multiply the x by 2. Now I'm gonna get a stack of ellipses because it's a number x squared plus y squared equals. It's still a paraboloid, but it's kind of been squished in. The slices in the z are ellipses. It's still a parabola and parabola, but this parabola is a little bit skinnier. Yeah, because there's a 2 in front of the x squared. We said that makes the parabola a little bit skinnier. But recognize there's no how the shape is. That would fit into this z not being squared. Okay, hyperbolic paraboloids. The difference between the paraboloid and the hyperbolic paraboloid is this minus in between the two squared things. So let's just go right to our piece here, and I'm going to throw a minus in front of this. Now, before we hit execute and see what it does, let's just, this might be small, but it's written as 2x squared minus y squared equals z. So it's something squared minus something squared equals z. If I make z equal to a number, now it's x squared minus y squared equals a number. That's a hyperbola. So slices like this, where I make z equal to, are supposed to be hyperbolas. If I make x equal to a number, then I'm getting upside down, because there's the minus in front of the y squared. I'm getting upside down parabolas. If I make y equal to a number, then I'm getting right side up parabolas. So slicing in the z, hyperbolas. Slicing in the setting x equal to a number, upside down parabolas. Slicing in the x, right side up parabolas. So now trying to imagine that, that's our hyperbolic paraboloid. It still has the parabola flavor, that's why it's paraboloid. But if I take a slice, I'm getting these slices in the z as being hyperbolas, hyperbolic paraboloid. Go back to the equation and notice that there's no more restriction on what z could be. I could pick any z value. If you pick z equal to a positive number, I could make y equal to 0, and I could hit, I could pick the x to hit that z. If you make z equal to 100, can I get to z equal to 100? Sure, make y equal to 0, x equal to 10. You can do it. You can pick a z value that's super negative, like, well, minus 100. Make x equal to 0, make y equal to 10. That gives me minus 100. So you can get all the positive z's, you can get all the negative z's. It's not restricted in its z value like the paraboloid, this hyperbolic paraboloid. If I put numbers in front, so like a number x squared, all that does is kind of squish the hyperbola a little bit, or stretch the paraboloids, however I want to think about it. The one that I've got drawn here actually has a 2 in front of the x squared. So these parabolas are a little bit skinnier than those upside down parabolas. If I get rid of the 2 to make it the same, then the parabolas will be plain. Those parabolas are the same width, the same skinniness as those upside down parabolas. And every time I take a slice, though, I'm still getting a hyperbola. All right. The two ones are these are the best ones here, my favorite. Hyperboloids of one sheet and hyperboloids of two sheets. The difference between the one sheet and the two sheet is the two sheets, hyperboloid of two sheets has two sheets. It's in two pieces. It's separated. Whereas hyperboloid of one sheet is all connected. So let's just make one. Oh, and in the equations, one sheet has one minus sign, two sheets has two minus signs. So let's put in a hyperboloid of one sheet. So I'm going to go, that's going to be everything squared, x squared minus y squared, it's all, plus z squared. So there's only one minus sign, equals 1. And here it is, a hyperboloid of one sheet. It's all connected together. Now, when I look at it like this, every slice is a circle. It's like a stack of circles. When I look at it like this, they're all hyperbolas. When I look at it like this, it's all hyperbolas. So two slices are hyperbolas, and one slice is a circle. Let's go back to the equation and see if we can see that algebraically. Okay, if I make x equal to a number, that's going to bring it over to this side, and it's going to become plus x squared if I make x equal to a number. And I picked the one that had the minus sign on it. Yeah, now whatever I pick for x, I'm getting some number squared plus some number squared equals a positive number. That's a circle. And it doesn't matter what value for x is, I always get a circle. So there's no like forbidden values. Yeah, every time I pick x equal to a value, I get a circle. But right in the middle here, that's the skinniest circle. Right in the middle here, that's the circle with the smallest radius. Yeah, that's when I make this, that's supposed to be r squared, the radius squared. And when I make x equal to 0, the radius squared is 1, the radius is 1. That's the smallest circle I could get. That's that circle in the middle. So it doesn't go through the origin. 0, 0, 0 is not a point because I can't get to it because the smallest circle doesn't collapse down at the origin. But anyway, I moved there was one minus sign, and I moved the variable that with the minus sign over, so I always got circles. Let's put it back. Okay, that was the original. If I move the piece with one of the, if I move the y squared or the x squared, if I move that over to the other side, one of the positive ones over to the other side, then I get minus something squared plus something squared is equal to some number. Now you pick a z value, that becomes a positive or negative number, but it's always a hyperbola. Because there's only one minus sign, there's only one variable squared that I can move over to the other side to make a circle. The other two are positive, so when I move them over, I leave the one minus sign and a plus sign, and that's giving me the hyperbola slices, whether I look at it like that or like that. These are these hyperbola slices. And there's no restriction on what z is equal to because, go back to the equation, if I pick z to be like a super big positive number, then that's a hyperbola minus x squared plus y squared equals a super big positive number. You can do that. Or the other way around, if it's a super big negative number, this side, then say this worked out to be minus 50. Then I could multiply that through by a minus sign, and I would get x squared minus y squared equals plus 50. That's just a hyperbola as well. Hyperbola of one sheet, one minus sign. Hyperbola of two sheets, two minus signs, and it'll be separated, two sheets. There'll be two pieces. So let's look at this a little closer here. Now I'm going to do the same idea. I'm going to put this, let's put this back the way it was. Put it back the way I found it. Okay, now there's two pieces with minus signs. So there's two choices to move this over here and get, well, if I move one of them over, let's move the x squared over. Now, whatever I pick for x, I get a hyperbola. If I move the y squared over, then it would be 1 plus y squared. If you move one of the minus sign, one of the minus squared pieces over, you get a hyperbola. So there should be a hyperbola, hyperbola. Let's put that minus one back. The sort of odd one out is this plus. If I move that over, the 1 plus, it becomes a negative. Now everything, oh, negative, negative, I'm going to multiply this whole thing through by positive, or sorry, by -1 just to kind of clean it up. If I do that, so if I move the one that's positive over, I end up getting something squared plus something squared equals a number. That's a circle, but z is sort of restricted, right? Z can't be bigger than 1. No. Z is restricted. Z can't be smaller than 1 because I want this side to be positive. So Z has to be either bigger than 1 or smaller than -1 to get a circle. So you have two slices. Let's put this back. I'll move this over to the other side. It was a positive. So make the x a number or the y a number, and I'm getting a hyperbola. Hyperbola slice, hyperbola slice. Make the z a number, and I'm getting a circle, but I'm getting circles above z equals 1 and below z equals 1. That's why it's of two sheets. You can't have a z value in between +1 and -1, so there's that whole region where the hyperboloid doesn't exist. That's why it's of two sheets. One sheet is for z bigger than 1, and the other sheet is for z less than 1. Okay, that was a lot of looking at the algebra and thinking about level curves. Let's just look at the picture. So I want two minus signs. Oh yeah, there it is. Circles in the red, circles in the blue, but they don't, it's two sheets, it's not connected. Where do we see the hyperbolas? Well, the hyperbolas are here. Anytime you pick an x, you're getting another one of those hyperbolas. Let's narrow down our window here. So I made x equal to 0, and there's my hyperbola slice. If I would have made y, shrunk down the y equal to 0, I would have got the hyperbola this way. Let's undo that. So there's a hyperboloid of two sheets. Okay, quadratic surfaces. Now this is again, you can look at the chart. If you're one of those people that love to memorize charts, I guess you can do that. I would recommend that you don't do that. I would recommend that you think about level curves and slices and think about how the equations relate so you understand it rather than just memorize it. It's going to super pay off. There's going to be one instance in your life where this picture shows up. Maybe you're in a different math class. Maybe it's on Jeopardy, something on the subway, I don't know. And you're going to be able to go, oh, a hyperboloid of two sheets. And you'll look like a genius. So, and also in this class, I want you to be able to use the terms, right? If I say, what kind of graph is this? I want you to be able to say hyperboloid of two sheets, hyperboloid of one sheet. There's our quadratic surfaces.